Welcome back. In this video, we're going to be looking at some example problems of calculating the area between two curves. Let's get to it. All right, so here's our first example. We want to find the area of the region bounded by the graphs of y equals 4x and y equals 6x squared. Okay, and so in order to find the area between two curves, we need to know the formula for the area between two curves. And that formula looks like this. The area is equal to the definite integral from a to b of the top function of the region f of x minus the bottom function of the region g of x, and that is multiplied by dx. And so before we can determine which of these two functions are the top and bottom functions, we first need to graph these two functions and get a visual of what this region is that we want to calculate the area of. But before we can draw that picture, what we first want to do is determine the bounds of integration. Between what two values of x is the region between these two functions located? And the way you determine that is to figure out where these two functions intersect, right? Because wherever they intersect, those are going to be the values of x of which your region lies between. And in order to figure out where they intersect, all we have to do is set the two functions equal to each other, right? We have y equals 4x and y equals 6x squared. And so if we replace this y with 4x and then solve for x, that will tell us the x values of the coordinate points where our functions intersect. Okay, and so if we do that, we will have that 4x is equal to 6x squared. And if we subtract 4x from both sides of the equation, we will have that 0 is equal to 6x squared minus 4x. And now in order to solve for x, I see that I can pull out a common factor of 2x from each of these terms, right? So 0 will be equal to 2x times what is left in each of these terms after dividing out 2x. And so if we divide 2x out of 6x squared, 6 divided by 2 will leave us with 3, and then dividing 1x out of x squared will leave us with just 1x. All right, and then if we divide negative 4x by 2x, negative 4 divided by 2 is negative 2. And if we divide this x by x, well, that x is just eliminated, and so that is the end of that quantity. All right, so now we have two factors that we can set equal to 0 and solve for x for. So we'll have 2x is equal to 0, and 3x minus 2 is equal to 0 as well. And so solving for x in each of these equations, we'll have that x is equal to 0, because if we divide both sides by 2, we still have 0 on that side. And if we add 2 to both sides of this equation, we'll have 3x is equal to 2, and then dividing both sides by 3 will give us that x is equal to 2/3. And so now we have determined that these two functions intersect at x equals 0 and x equals 2/3. These are the two values of x of which our region lies between. All right, and so now that we have determined the values of x where these two functions intersect, let's draw a graph of these two functions. And so I'll draw the y-axis here and the x-axis, and then I'll label them. So this is the y-axis, and this is the x-axis. And then what we will do is graph these two functions. I'm going to start with y equals 4x. We know that y equals x is just a diagonal line with a slope of 1 that crosses through the origin. And so 4x will be that same line except with a slope of 4. And so if this line right here is x equals 1, and this line right here is y equals 4, then our line y equals 4x will look like this. And so this is our line y equals 4x. Okay, and so then let's graph y equals 6x squared. And so we know that y equals x squared is a parabola. Now that 6 might compress it a little bit, but we do know that these two functions intersect at x equals 2/3. And so you'll notice that I have 3 sections between x equals 0 and x equals 1. So x equals 2/3 would be right here. So our parabola for y equals 6x squared should intersect right about here with our line y equals 4x. And so our parabola will look something like this. Okay, so that's going to be y equals 6x squared. And so now we can see that the region that we want to calculate the area of is this region right here between these two functions. And so I'll shade that region in. This is the region that we want to calculate the area of. And so now that we have our graph drawn, and we know where the two functions intersect at x equals 0 and x equals 2/3, we are now ready to set up our definite integral to calculate the area of that region between the two curves. All right, so all that's left is to determine which of these two functions is the top function, f of x, and which of them is the bottom function, g of x. And so if we look at our region here, which function, if we look from the top down, is on the top of that region? Well, it looks like this line, y equals 4x, is on the top of the region, and this parabola, 6x squared, is at the bottom of the region. And so we can determine that y equals 4x is f of x, and 6x squared is g of x. All right, and so if we clean up our work, and remember that x equals 0 and x equals 2/3 are our bounds of integration, then we can set up our definite integral to represent the area of that region. And so we'll have that this is equal to the integral from a to b, or from 0 to 2/3, of f of x, which we determined is 4x, that's our top function, minus g of x, our bottom function, 6x squared. So we'll have 6x squared times dx. All right, and so now we have a definite integral that we can solve to find the area of that region. And so if we integrate both of these terms with respect to x using the power rule of integration, we will have that this is equal to the integral of 4x, which the power rule of integration says that you add 1 to the exponent and then divide by that new exponent. So we'll have 4 times x squared divided by 2 minus the integral of 6x squared. And so if we add 1 to the exponent and divide by that exponent, we'll have 6x cubed divided by 3. And that will be evaluated from 0 to 2/3. Okay, and so now what we want to do is plug in 2/3 into this expression and subtract plugging in 0 into this expression. But before we do that, notice that 4/2 and 6/3 can be reduced, and so this will be equal to 2x squared minus 2x cubed, evaluated from 0 to 2/3, right? 4 divided by 2 is 2, and 6 divided by 3 is 2. And so now if we plug in 2/3, we will have that this is equal to 2 times 2/3 squared minus 2 times 2/3 cubed. And then we want to subtract plugging 0 into this expression. But note if we did that, 2 times 0 squared is 0, and 2 times 0 cubed is also 0. So we're really just subtracting 0, and that's not going to affect the rest of our calculation. All right, but if we clean up our work here, we can simplify our answer and find that this is equal to 2 times 2/3 squared, and 2 squared is 4, and 3 squared is 9, so we'll have 4/9, minus 2 times 2/3 cubed. Now 2 cubed is 8, and 3 cubed is 27, so we'll have 8/27, and then we don't need to write that minus 0. All right, and so then we'll have that this is equal to 8/9 minus 16/27, and if we multiply 8/9 by a form of 1 of 3 divided by 3, then we'll have that this is equal to 24/27, and then we'll be subtracting 16/27, and that will be equal to 8/27. All right, and so 8/27 is the area of this region between these two curves. For our next example, we want to find the area of the region bounded by the graphs of x equals 2 minus y squared and x equals y squared. All right, so this is a little bit of a different problem. Instead of giving us equations in terms of x, we have been given two equations in terms of y. Now, this isn't always the case, but because they are given to us like this, we are probably going to want to integrate with respect to y to find the area of this region. Okay, but before we get that far, let's just start by determining what the graphs of these functions look like. And so let's start by determining where they intersect, and that should help us figure out what the bounds of integration are going to be. Now in this case, since both of these equations are given to us in terms of y, I'm going to set them equal to each other in terms of y and just replace this x with this function, right? So what we're going to have is that 2 minus y squared is equal to y squared. And so if we move all these terms onto one side of the equation by subtracting 2 and adding y squared to both sides, what we'll have is that 0 is equal to y squared plus y squared minus 2. And so these two terms will combine since they are like terms, and so we'll have 0 is equal to 2y squared, and then we'll still have minus 2. Okay, and now what we want to do is solve for y, and that will tell us the y values of the points where our functions intersect. And so in order to do that, notice that we have a common factor of 2 in each of these terms, and so if we pull that out, we'll have that 0 is equal to 2 times y squared minus 1. And now what we have here is a difference of squares. y squared minus 1, and 1 is the square of 1, and so we can factor that and have that 0 is equal to 2 times y plus 1 times y minus 1, right? That is how we factor a difference of squares. And so now if we set these two factors equal to 0 and solve for y, we'll have that y plus 1 is equal to 0 and y minus 1 is equal to 0, which gives us that y is equal to negative 1 and y is equal to positive 1. All right, and so now we have determined that at y equals negative 1 and y equals 1, these two functions will intersect. And so now let's draw a picture of these graphs. Let's see exactly what they look like and what the region is that we want to calculate the area of. And so let's start by drawing the y-axis, and then I'll draw the x-axis here. And so I'll label them. This is y, and this is x. And now let's start by graphing x equals y squared, and then we'll get to our other equation. But x equals y squared is just going to be a basic parabola that points in the positive x direction. And so what I mean by that is that it will look like this. Right, that is the function x equals y squared. So I'll label that as x equals y squared. All right, and so then what about this function? We have x equals 2 minus y squared. Well, this is also a function that has y squared in it, except it's negative, and so that means it's going to be reflected. And so instead of pointing in the positive x direction, the parabola will point in the negative x direction. And then this 2 right here is telling us that the parabola is shifted 2 units right in the x direction, or 2 units in the positive x direction. And so if we say that this is x equals 1 and this is x equals 2, then our parabola will look like this. That will be x equals 2 minus y squared. Okay, and as you can see, if this is y equals 1 and this is y equals negative 1, that these two functions intersect at y equals 1 and y equals negative 1, just like we found right here. And so the region that we want to calculate the area of is this region right in here between these two curves that we just graphed. Okay, and so now just from a quick glance, it should be pretty obvious now that we do want to integrate with respect to y to find the area of this region. And the reason I say that it's obvious is because if we were to do it in the x direction, right, if we were to look from the top down, notice that the top and the bottom functions are not the same for the whole region, right? We would have to use two integrals because up until x equals 1, the top function of the region is x equals y squared, and it's also the bottom function. But then after x equals 1, the top function is this parabola, and the bottom function is also that parabola. So the top and bottom functions are switching on us, and they're not staying the same, so we don't want to have to integrate with respect to x if we don't have to. Luckily, if we look in the y direction, or from right to left, notice that the top function, or the right function, is the same function for the whole region, and the bottom function, or the left function, is the same for the whole region as well. All right, so we can see that the top function, or the rightmost function, is 2 minus y squared, and the bottom function, or the leftmost function, is x equals y squared. And so now we can set up a definite integral to represent the area of this region and calculate its area. And so if we clean up our work here, we know that the area between two curves with respect to y is the definite integral from some value of yc to another value of yd of the top function or the right function f of y minus the bottom function or the left function g of y, and that is multiplied by dy. All right, and so for this scenario, this will be equal to the definite integral from negative 1 to 1, right? Those are the two values of y of which this region lies between, right? Our bounds are not going to be in terms of x because we are integrating with respect to y. So our bounds also need to be values of y. So we're going from negative 1 to positive 1. And then our top function is 2 minus y squared, and our bottom function is just y squared, and so we will subtract y squared and then multiply by dy. All right, now negative y squared and negative y squared will become negative 2y squared. So I'm just going to rewrite that here. We will have negative 2y squared times dy. And so now if we integrate with respect to y for both of these two terms, we will find that this is equal to 2y, right? The integral of a constant is just equal to that constant multiplied by the variable of integration, which is y in this case, minus 2y cubed divided by 3, right? Using the power rule, we add 1 to the exponent and divide by that new exponent. And this will be evaluated from -1 to +1. All right, so then plugging in 1 into this expression, we will find that this is equal to 2 times 1 minus 2 times 1 cubed divided by 3, and then we will subtract plugging in -1 into this expression. And so we'll have 2 times -1 minus 2 times -1 cubed divided by 3, and then that is it. And so if we clean up our work here, we can simplify, and this will be equal to 2 minus 2/3, and then we will subtract -2, and then subtract 2 times -1, because -1 cubed is -1, so we'll have -2 divided by 3. But these two negatives will cancel out, and so what we'll actually have here is plus 2/3, and so I'll write that there. Okay, and so then if we simplify again, 2 is the same as 6/3, and so 6/3 minus 2/3 is equal to 4/3, and then we will be subtracting -2 plus 2/3, and that will be equal to -4/3. And so then this negative and this negative will cancel out, so we'll have 4/3 plus 4/3, and that is equal to 8/3, and 8/3 is the area of this region between these two functions. All right, so for our next example, we want to find the area of the region bounded by the graphs of y equals x to the 4th power and y equals the absolute value of x. Okay, and so the first thing that we want to do to find the area of the region between these two functions is determine where they intersect. Now that's not going to be as easy this time because we have an absolute value function, but thankfully that's a pretty easy function to graph, and so maybe we can just determine where these two functions intersect by just graphing both of them on the same coordinate plane. And so let's do that. Let's draw the y-axis here, and then let's draw the x-axis. And so I'll label them. Here's the y-axis and the x-axis. And now let's start by just graphing y equals the absolute value of x. We know that the absolute value of x is equal to the following piecewise function, where you have positive x for values of x greater than or equal to 0, and negative x for values of x less than 0. And so what that means is that for all the positive values of x, on this side of our coordinate plane, we will have the line y equals x, which is a diagonal line with a slope of 1. And then for all the negative values of x, on this side of the coordinate plane, we will have a line with a slope of -1. And so what that will look like is that on the positive side, we will have this line, and on the negative side, we will have that line. All right? And so this right here is the function y equals the absolute value of x. Okay, and so before we graph the next function, let me just label some values along each of our axes. Let's say that this is y equals 1, this is x equals 1, this is x equals -1, and this is y equals -1. Okay, and so now let's graph y equals x to the 4th power. Now similar to x squared, x to the 4th power is a parabola, and it's actually pretty simple to figure out where this intersects with the absolute value function, because if you plug in 1 or -1 into this equation, you will output 1, right? Y of 1 will be equal to 1 to the 4th power, which is just equal to 1, and y of -1 is equal to -1 to the 4th power, which is also equal to 1. And so we have two coordinate points of 1, 1 and -1, 1, which are here and here. And so that is where y equals x to the 4th power is going to intersect with the absolute value function. And so if we draw that parabola, it will look something like this. That is our function y equals x to the 4th power. And so now we can see that the region bounded by these two graphs includes this region right here and this region right here. And so the area that we want to calculate will be the area of this region and this region. All right, and so in order to calculate the area of the region between these two functions, we're actually going to need to use two definite integrals. And the reason is that even though y equals the absolute value of x is the top function for the entire region that we want to calculate the area of, at least with respect to x, this line for positive values of x is positive x, but this line for negative values of x is negative x. So we technically have two different functions for the top of the region. Okay, and now I know I said before that you want to try to avoid using two definite integrals if at all possible, but in this case, because we're working with the absolute value of x, we cannot avoid using two definite integrals, at least by traditional means. If we recognize symmetry, then we can get around that, but I'll talk about that in a little bit. But for now, let's just set up two definite integrals, and we will start with our first integral by looking at this first region here from -1 to 0. So the area will be equal to the definite integral from -1 to 0 of the top function, which will be negative x, right? We have the absolute value of x as this top function, but this side of it is negative x for the negative values of x. So we have negative x minus the bottom function, which is y equals x to the fourth power, because that is on the bottom of our region when looking from the top down. So we have minus x to the fourth power. And so that is multiplied by dx, and then we will add that to the definite integral from 0 to 1. Now we're looking at this region right here, where the top function is positive x, right? Where the x values are positive. So we will have x minus x to the fourth power, because x to the fourth power is still the bottom function for that part of the region, and that will also be multiplied by dx. Okay, so now if you wanted to, you could solve both of these definite integrals and find the area of the regions formed by these two functions, but there's actually an easier way here. Note that because both the absolute value of x and x to the fourth power are symmetric functions, right? They are going to be the same shape on either side of the y-axis. We can actually just calculate the area of 1/2 of this region and then multiply it by 2, and that will account for the entire area of both parts of the region. And so I'm just going to take the easier integral here, the integral from 0 to 1 of this expression, and multiply it by 2 to get the area. So I'm going to erase this first integral, although what we had here would still give us the same answer. I'm going to multiply this integral by 2, and that is what the area will be equal to. All right, and so let's work with that. Let's clean up our work a little bit. And if we integrate both of these terms using the power rule of integration, we will have that the area is equal to 2 times x squared divided by 2, right? We add 1 to the exponent and then divide by that new exponent, and then subtract x to the fifth power divided by 5. And that will be evaluated from 0 to 1. All right, and so now we'll plug in 1 into this expression, and then subtract plugging in 0 into this expression. And so this will be equal to 2 times 1 squared divided by 2 minus 1 to the fifth power divided by 5, and then we will subtract plugging in 0 into this, but notice that 0 squared divided by 2 is just 0, and 0 to the fifth power divided by 5 is also 0, and so we're just subtracting 0, but we don't really need to worry about that too much because it's not going to affect our calculation. All right, and so then what we'll have is that this is equal to 2 times 1/2 minus 1/5. And so then if we distribute this 2 through this quantity, 2 times 1/2 is just equal to 1. And so this will be equal to 1 minus 2 times 1/5, which is 2/5. And 1 minus 2/5 is equal to 3/5. And so 3/5 is the area of these two regions that are formed between these two functions or these two curves. All right, and so this was kind of a funky example, but it just goes to show you that if you can recognize symmetry, it makes calculating the area a lot simpler because you can just multiply the area of 1/2 of that region by 2 and you'll get the same answer. I wouldn't recommend doing this for most problems because you're likely to make a mistake, but if you're working with an absolute value function and another symmetric function, this is a pretty easy way to get around doing multiple integrals and wasting a bunch of time. All right, so hopefully this method will save you some time and was kind of neat to see a different way of calculating the area between two curves. All right, so for our last example, we have if R is the shaded region below, this area right here, then A, set up an integral or integrals in terms of x that represents the area of R, and B, set up an integral or integrals in terms of y that represents the area of R. Okay, so we're given a graph here where we have the line y equals 1/2 times x and a parabola of y equals 3 minus x squared. And then we can see that the points of intersection for these two functions are -2, -1 right here, and 3/2, 3/4 right here. All right, and so let's start with part A. Let's set up an integral, or possibly multiple integrals, in terms of x that represent the area of R. All right, so when we want to set up an integral in terms of x for this area, we want to look from the top down, and our bounds of integration need to be values of x for which this region lies between. So the area will be equal to the definite integral from some lower bound of x to some upper bound of x. And so let's look at this region. What values of x does it lie between? Well, it goes from -2 to this point right here, which the x value is 3/2. So our lower bound is -2, and our upper bound is 3/2. All right, and so now let's determine what our top function is and our bottom function, because we're going to have the top function minus the bottom function in our integral here. And so the top function, if we're going from the top down, is this parabola, right? For this whole region, this parabola is the top of the region. And so y equals 3 minus x squared is our top function. So we'll have 3 minus x squared, and then we will subtract the bottom function, which for this region R will be this line right here, right? The whole bottom of this region is this line, y equals 1/2 times x. And so we will subtract 1/2 times x and then multiply by dx. Okay, so this is the solution to part A. This is one definite integral in terms of x that represents the area of R. But now let's work on part B. Let's set up a definite integral in terms of y, or multiple integrals, that represents the area of this region. And so if we're going to work in terms of y, we first need to get both of our functions in terms of y as well, right? Currently, they are both in terms of x because we have y equals and then some expression that is in terms of x. And so what we need to do is solve for x in both of these equations, and then that way they will be in terms of y. And so let's start with y equals 3 minus x squared. If we add x squared to both sides of the equation, we will have y plus x squared is equal to 3. And then if we subtract y from both sides of the equation, we will have that x squared is equal to 3 minus y. And then if we take the square root of both sides, then we will have solved for x. And so if we do that, we will have that x is equal to plus or minus the square root of 3 minus y. And it's important to have that plus or minus there so that we have both the positive and the negative side of this square root function, right? If we ignored the negative side, just the positive square root of 3 minus y would be 1/2 of this parabola. This other side is when that square root is negative. Okay, so it's important to remember that there are two sides to that square root function, so that it is still the same function in terms of y that it was when it was in terms of x. Right? These are the same function, just in terms of different variables. Okay, so that's one of our equations, but now let's solve for x in this equation. We have y equals 1/2 times x. If we multiply both sides by 2, then we will have that x is equal to 2y. And so that one was a lot easier to get in terms of y compared to our previous equation. All right, but now that we have both of them in terms of y, we are now ready to set up our integral or integrals in terms of y to represent the area of this region. Now, this is going to be a little bit more tricky than it was in terms of x, and that is because when we are looking at our region and we are determining which function is on the top or which function is on the bottom, we're not going to be looking from the top down like we were in terms of x. Instead, we're going to be looking from the right side of the region to the left side. Okay, so notice that our region is contained between the y values of y equals -1 and y equals 3. However, if you notice, as we go from right to left along those values of y between -1 and 3, the rightmost function, or the top function, is not the same for the whole region, right? If we start up here at y equals 3, and we move from right to left, and we continue to go down along the y-axis, once we hit this intersection point right here at y equals 3/4, the rightmost function, or the top function, changes. Up until this intersection point, the rightmost function of this region has been this parabola. But once we move to the y values below this intersection point, now when we move from right to left, the function on the rightmost side of the region is this line, x equals 2y. Okay, and so the rightmost function, or the top function, for this region in terms of y is not the same for the entire region. And so to kind of help you visualize this, we can split this region into two sections. We have an upper section from y equals 3/4 to 3, and then another section from y equals -1 to y equals 3/4, right? Because each of these sections is going to have a different rightmost function. Now both sections still have the same leftmost function, or the bottom function, of this parabola, but we still have a change in the rightmost function, and so because of that, we are going to need to use two definite integrals to represent the area of this region in terms of y. And so let's start with the lower region. If we're going to set up two definite integrals, we'll have that the area is equal to the integral from y equals -1 to y equals 3/4, right? That is going to be this region right here, from y equals -1 to y equals 3/4. And if we move from right to left, the top function, or the rightmost function, is the line x equals 2y. So we're going to have 2y minus the bottom function, or the leftmost function, which if we move from right to left, will be this parabola. And so we will be subtracting the negative side of this square root function, right? Positive square root of 3 minus y is this side of the parabola, and the negative square root of 3 minus y is this side of the parabola. And so we will be subtracting the negative side, and so we will have negative square root of 3 minus y, and then times dy. Now these two negatives will cancel each other out to become positive, and so I'm going to change that to be a plus sign. And now this integral right here represents the area of this bottom section of this region. And so we need to add a second definite integral to represent the area of the top part of the region, the other section. And so that is located from y equals 3/4 to y equals 3. And so our bounds of integration will be 3/4 to 3. And our top function, or rightmost function, is now the positive side of the parabola, right? When we move from right to left, we hit that function first. And so we will have the square root of 3 minus y minus the bottom function, or the leftmost function, which when we move from right to left is the negative side of the parabola, or the negative side of the square root function. And so we will subtract negative square root of 3 minus y times dy. Now once again, these two negatives are going to cancel out to become positive, and so I'll erase that, and we will have a plus sign. But note that these two expressions are the same, and so we can combine them to be 2 times the square root of 3 minus y. And so I'm going to rewrite this definite integral, and we will have 2 times the square root of 3 minus y times dy. And now we have a definite integral that represents the area of the top part of this region. And so now, adding that area to the area of the lower section of that region now completes the entire area of that whole region R. Okay? And so these two definite integrals are the integrals in terms of y that represent the area of the region. And so that is our answer for part B. Okay, so hopefully this example was a good demonstration of the differences between calculating an area in terms of x or in terms of y. Obviously, if we were actually going to calculate the area here, we would want to work in terms of x because we only have one integral to work with. We wouldn't need to use two integrals like we do in terms of y. Okay, so I hope this serves as a good reminder that sometimes it's going to be easier to integrate with respect to one variable rather than another when calculating the area between two curves. All right, and so with that, that is all I had for this video. If you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now, so I will see you next time.